Hello there! Right, derivations. Nobody likes derivations. Well, I like derivations. What is a derivation? It's when you start with one mathematical rule or law, and by substitutions and rearrangements and derivations, you actually, without breaking any rules of logic, equate something new to something that you're more familiar with. Now, the derivations that we see in physics are, to varying degrees, quite tricky. The simple ones that we do in AS physics soon build to really quite complicated ones. And yet nearly all of the laws of physics that we know about have to fit in, have to be able to be derived from the basic principles for us to believe that they're to be correct. Now, one of the hardest derivations that you could ever attempt is E equals mc². Now, E equals mc², I think, is within your ability at this moment, so why not have a go? Can you derive E equals mc² from basic principles? It's tricky, but you can do it. Now, one of the most impressive things that you can do as a physicist is derive Einstein's famous mass energy equivalence law, E equals mc². It's not a difficult law to understand and see where it comes from. I mean, why does E equals mc²? Well, it's really quite simple. This idea that a mass changes when an object gets very close to the speed of light means that an object's mass at a given velocity is scaled by this thing that we call the Lorentz contraction, which is a scaling factor that means that it spikes over to infinity as v goes to c. So from here we're going to get E equals mc². And it's a little bit long-winded, but if you can do this derivation, I guarantee it, people will be impressed. They'll be like, whoa. Right, okay. So the first thing we need to do is square both sides of this relationship. So it's going to be m² is equal to everything on that side squared. m0 over 1, the Lorentz contraption. That all gets squared. Let's do it. And so if we square it and rearrange it, it becomes m² 1 minus v² over c². Squaring it cancels the square root, and then we've multiplied both sides by this same thing, so it brings it over to this side. I hope you can see that that's the same relationship that I've just stated above. Now, we're going to multiply both sides by c², and we get this relationship going on. Well, first of all, let's rearrange this out first before we do that. m² times 1 is going to be m². m² times all of that, well, let's do it. It's m² times v² over c², and that all comes out as m0². So as I said, we're going to multiply both sides by c², so it's going to be m² c². Now, if we multiply this by c², it simply becomes minus m² v², because divided by c times by c² is, cancels out. And of course this goes over to both sides. This m0² also has a c². Following? Good. Okay. I'm going to rearrange it, so I'm going to take this section over there, I'm going to add a half, minus m² v² on both sides. So we get is m0² c² plus m² v². Simple? Now, because we talk about a situation where m0 squared c², that's just a constant, isn't it? That's not going to change. So we're going to represent that as a constant from now on. So I can say that m² c² is m² v² plus a constant. Why would I want to do that? Because I'm about to derive it with respect to time, and because this thing is a constant, its derivative is going to pop out as 0, because it's not dependent on time. So if we derive this with respect to time, d by dt of m² c² comes out to be, do it to both sides first before we carry on, plus this constant that is also derived, It pops out that the c pops out of both of these, so put the c in front so that we're not deriving the wrong thing. dm squared by dt, and d, that's going to go to 0, so we forget about that. m squared v squared with respect to t. Take a good look, about to turn the page, because I've run out of paper. Okay, in fact I'll pull this one off. There we go, and I'll put it there so you can see where I'm continuing. So let's do that derivation. What is m squared? Oh my word, it's 2m. Brilliant. Right, so c squared, 2m dm by dt has got to be equal to, you can see what I'm doing, I'll lift it up a bit, has got to be equal to, what was I doing, 2mv, let's derive this side, that's it. Now very simple laws of derivation rules applying here, nothing fancy. However, we do know that over here, that the rate of change of mv with dt is the force. It's the rate of change of momentum with time. This is force. This is Newton's second law. Remember, force is ma in that special case, but more unspecialised. The force is the rate of change of momentum with time. So therefore, that can all just disappear somewhere, and we can be happy. So where were we? Right. Before we no, let's do it now. So c squared goes to 2m dm over dt, 2mv multiplied by the force on that side, because that's all the force. Okay, so the next thing that we're going to do is, well, we've got 2m on both sides, so let's divide through by 2m. Okay, so it becomes c squared is dm by dt goes to v times f. I'm going to stick the f in front for reasons I'm about to explain. We understand and we have seen before that the rate of change of energy with time is equal to its force times its velocity. This you've seen on one of the other videos that I've shown. It basically comes from the idea that this is work is force times distance, so the rate of change of work is force times the rate of change of distance with time, and that's velocity. And so we know this relationship to be true. The rate of change of energy is force times velocity. We have force times velocity, so we can say quite happily that c squared dm by dt is equal to dE by dt. Alright, let's divide by d by dt on both sides, and we get mc squared equals E. Prove that mass and energy are the same thing. Now, if you can derive that, then you can do most things in physics.